We're recording? All right. All right. Good evening, everyone. Thanks for being here, especially in such a cold and gloomy night. Let's warm ourselves up with a little bit of architecture and AI, if you may. I would like to welcome tonight Stanislas Chaillou. He was kind enough to accept an invitation to talk here and share some of his work and his interest tonight with us. Us folks who are technology-oriented, design-oriented, and we like to think about what are the possibilities at the intersection of computation, code, and creativity. I think I'm very excited about this talk because his recent work has reached out many domains. It's reached a lot of depth, and a lot of people are echoing a lot of his latest achievements. So I think it will be a really interesting one. He's a little bit of his background. He's natively from Paris, like good French people. And he has studied very internationally in Zurich, in Lausanne, and very recently here at the GSD. He's a recent grad from the MArch program. And but his interests cover a wide range of fields. And he has worked in Flux.io, which was a San Francisco startup that tried to connect design tools through data and simultaneity. And now he's one of the leaders of the R&D department at Spacemaker.AI, whose work he may or may not share today with us. I don't know how secretive still it is, but I'm very excited to hear about it. So without further ado, please join me in welcoming Stan.
Yeah, you think it's working? Is this okay? Awesome. Great. Okay, great. Good evening, everyone. My name is Stanislas. I'm a data scientist and an architect at Spacemaker.AI. First of all, Luis, thank you for the invitation. It's great, both for the company, but also for me to be able to talk a bit about the thing I've done in the past, my research, but also Spacemaker in general. And I know Spacemaker is a bit secretive about the thing we do, so I'll try to share things we do. And I'm happy to answer questions at the end, whether you want to know what we do in more detail or if there are things that I'm covering that are unclear. And I'm really happy to, anyway, answer questions. We'll do Q&A at the end, I know. So the point of the talk of today is to really dive into this notion of the overlap between AI and architecture. There is today an intersection. It's recent. It's been 3-4 years that those two fields actually have like connected into something that is actually meaningful, both for the discipline, but for the idea of conception as a whole. And I think since I graduated from here and I had the chance to do my thesis on that topic, the point of talking to you tonight is to say that in academia, we have a chance to shape this thing. It's not just in the industry, as opposed to many changes that are happening today that have to be done in the industry. Like this could be done in academia. You can push the envelope through your work and your thesis if you want to, and tackle that thing, the plus here, between AI and architecture. So just to be very clear, I'm going to describe quickly my career path just because it reflects a thing that's happening at large in the industry. And maybe you already know people who have the same career path. The idea here is that we are a whole bunch of people bending our career path today to this reality of AI and architecture being closely tied together. So I started at EPFL in Switzerland. I did the most traditional architecture bachelor you can think of. I started to use parametricism, so Grasshopper or Dynamo, the softwares you all know. And then I moved on to work at Shigeru Ban in Tokyo, where I was in charge of the parametric practice. So I did a lot of structural optimization, working on wooden structures. So it was my first encounter with the notion of parametricism. So I don't know if everyone is an architect here, but for the sake of explaining what parametricism is, basically it's the idea that any design step, any design process can be turned into a set of rules that we can explicitly declare and set into an algorithm. So some of you know Grasshopper, some of you know Dynamo, but for those of you who have no idea of what that is, it's simply a way to translate an intuition of what a design step is into a script, into a graph. And so anyway, at Shigeru Ban, I started to work on this, and in the industry at large, there are armies of people doing this, trying to find and to encode what are the underlying rules of architecture. But the thing is, you can't encode everything. There's a whole bunch of rules, a bunch of realities that can't be just explicitly declared and set into a workflow. And by the end of that internship, I basically found out that there was a way to do better, maybe. And maybe we could find other technology that could help us tackle those rules and turn the rules into something more tangible, or something that could tackle a bigger breadth of options and parameters, maybe. So that was the reason why I came to Harvard. So when I came here, I did my MARC. I spent half my time studying architecture and half my time going to MIT and also going at the Paulson here to take data science classes, machine learning, AI classes, etc. And by the end, I did a thesis that maybe some of you guys have already seen. I'll go through it later. That kind of investigated the intersection between those two things. How can we use AI algorithms, AI models, to design buildings, and what does this change? Why is it a paradigm shift as opposed to what we used to do with parametricism? During the same time at the GSD, I went to work for Flux, as we said. It was like the first effort of Google to tackle, the challenge of the construction industry, and it later pivoted into Helix. So I worked 2 summers for them, working on machine learning application to construction problems. And the culminating point is today. I'm working for Spacemaker. So we are a Norwegian company. We're based in Oslo, but also have an R&D office here in Boston. And at the R&D office, we work on AI models to tackle midterm to long-term research projects. So I'm going to explain all of this. But the whole point of this slide is to say a lot of us are just bending our career path to match this reality that AI is actually coming to the field. I wouldn't have taken that path if that reality would be something theoretical and that would have no translation into actual meaningful steps to be taken. So again, I'm not the only one to do this today. We are a whole bunch of people trying to change our career path to match this reality. So now reflecting at the idea of doing architecture today, you can think of architecture as being a design discipline, of course, and it is. But it's also at the same time a game of mitigating constraints. So as any architect knows, you get provided with a brief, with a client, with a site, with a geography, with so many constraints that by the end of the day, the whole point of your project is also to mitigate those constraints and to bring them together into a design. And in fact, what makes the style of an architect, his personality as an architect, is the way to mitigate all those constraints, to bring them together, and to have his or her own way to answer the brief and all the constraints. You could think of this also as being a mix between a variable part and a fixed part. So what I mean by that is the fixed part is there is an underlying set of rules that we all share as architects. We just maybe don't know it, or sometimes we do, and we share it in the form of knowledge in academia. But there's very much a baseline that we all share as architects. And then there's the variable part, our style, our own way to go at mitigating those constraints. The point of the talk today is to talk about the fixed part, is the part that we could all share, that is universal to the discipline, and that could be potentially tackled through some amount of systematization. So algorithms, AI models, and all those things are here actually to help us coin down those moments, those commonalities in the design process. And in fact, it's been an ongoing effort. AI is absolutely not the newest trend, the newest thing. There's been an ongoing effort at finding a way to encode those design steps and finding the way that we can turn a design brief into a sequence of steps. So this is the most confusing slide I have tonight, but it basically shows you how to lay out an HVAC system. So HVAC, it's like those pipe and ducts you have at the ceiling running air. There's a way to lay out those things. You could literally turn the idea of laying out an HVAC system into a starting point and a sequence of steps and decisions. Steps are those like tiny boxes you see everywhere, and decisions is a way to go from one box to the next, from one decision, from one step to the next. So the notion of parametricism simply says, how do I turn any design brief into a sequence of steps I can go down, and basically it's a logic tree. So the same way this graph says there's a start point and an end point to lay out an HVAC, parametricism said, well, there's a way to go about drawing a building that could be turned into design steps and decisions to go from one step to the next. It actually went one step further and said to each decision, we can actually tie a parameter. So as I tweak the parameters, I change the value of those parameters attached to decisions, then the output at the end will change. You all know this, I'm sure, but it's still important just to rephrase it, to be clear about it, because that's the premise that is amazing about parametricism, but it's also the flaw that there is in parametricism. There's 2 questions that we should ask. When I write a script, is the script holistic, and is it pertinent? So it's very simple. When you draw a given script, when you draw a given sequence of steps, are you holistically setting up the problem? By that I mean, any script basically sets you up to be able to tackle a certain breadth of option. In mathematics, they call this the problem space. So as you draw your graph, at the end, the output you would get will belong into a problem space, will belong to a given breadth of option. To any given script, like corresponds a given breadth of potential option you could get out of it. There's no way, when you set up a parametric script, to know whether the script is holistic, to know the breadth that you're actually exploring by the end. The second problem is the question of pertinence. Since there is a parameter attached to each decision, well, it's your job as an architect to tweak the parameters to walk into the problem space, to search for the best option, or let's say good options. The only problem is that how do you know whether it's pertinent when you tweak them where the best spot is going to be? If you think about the problem space I was mentioning, where is the best spot in the problem space? So the way we used to do it, and that's kind of the limit of parametricism, is we can rely on the machine and we can turn to optimization and say, can the machine look into the balance of parameters and help me walk through the problem space to find maybe not the best solution, but at least the sweet spot in the problem space. So is my script holistic and is my script pertinent? The crucial thing in parametricism is that we can't answer both questions. We have no idea whether the design space is completely tackled, and we are quite unable to say whether the space we're exploring within the problem space is actually the right one. So parametricism remains an amazing tool. It's still a way to encode and to automate few steps and things we do every day as architects. It's not sufficient, absolutely not sufficient to tackle the biggest things and the hardest things that we have to do as architects. And that's the whole point of turning to AI and to machine learning. So let's step back a second from architecture and think about statistics. So the whole notion of AI and machine learning is to say, I'm going to use statistical modeling to understand a phenomenon. So you could think of a building as being a phenomenon. You could say parametricism was simply a way to understand and replicate a building or that phenomenon that a building is. Statistics says, well, the phenomenon is just a collection of observation, of data points flowing in space. So if you think about a building, it could simply be, I have a floor plan, I have elements floating in space, walls, rooms, columns. All of those are observation and things floating in space. Instead of trying to find a rule that explains for each column, each wall, each room, why is this thing like it is, I'm just going to look at the holistic view as the entire phenomenon and try to find characteristics and properties of the entire phenomenon, of the phenomenon as a whole. So this is a statistical distribution. So when we do statistics, we simply try to find characteristics of the distribution. So for this given distribution, we know that within one standard deviation from the mean, you have 34.1% of the points. Well, but as you see, I'm not trying to explain every single point within the distribution. I'm just trying to characterize the shape of the distribution and what that means. And that is the rule. So we flip the notion of rule from being something that explains every single thing to the rule being a property of the broader phenomenon. That's the very notion behind AI, and this is how we can tie it back to architecture. The building is a phenomenon. We study the phenomenon through the lens of statistics. And now let's go from the high-level picture to something very granular, very simple, down to earth and close to us. This is a training sequence. So the whole notion of AI and machine learning is to say, well, I'm going to show a given statistical model some amount of data. In this case, every data point, everything I'm going to show to my model is in fact an image of a floor plan. And my model over time is going to build the ability, the intuition to draw a floor plan. So this sequence is basically this image. So the training is this moment where we show the algorithm or the model how to draw things. Well, the training starts all the way at the top and ends up all the way down there. And what you see very clearly is as the model looks at the image and changes its, what we call the weights, so its ability to understand the phenomenon, is progressively building some amount of intuition of what is a floor plan. So if we go step by step, at the very beginning of the training, as he has seen only few plans, so this is after maybe 2 hours of training, I'm asking the model to generate its best guess of what a floor plan would be. And that's the best guess of the model. It's just a dumbed down box. Is only understanding for now, and it's only after half an hour, that a building, let's say a floor plan, is only a footprint. There's no notion of walls, no notion of rooms, no notion of like structure, nothing, just footprint. If you wait for another 2 hours and you ask for the best guess, then you get something a bit more granular and some amount of intuition is being inbuilt in the model. So now he's able to think about the walls, think about also where the openings, so the windows or the entrance doors. He's also able to think about program. So the color encodes the program. Red is going to be for bedrooms and green for living room. If you think about it, the programmatic layout here makes no sense. There's no in-between partition between the rooms. That strip here simply says, well, you have a living room that is like 50 centimeters thick, which makes absolutely no sense. But there's some amount of intuition that, well, we need to infill the plan, right? If you wait another 3 hours, then you start seeing some amount of logic in the adjacency. So by that, I mean, as we refine the intuition of the model, it has seen way more plans and way more often. Then suddenly it starts to think about the relationship of things in space. So this is the kitchen, this is the living room, this is a bedroom, this is way too tiny, then another bedroom and a piece of living room shoved into 2 bedrooms. But the notion is it's starting to understand that there's a logic to how you lay out things in space and how those things relate in space. At the same time, there's another thing which is really exciting is that it's starting to understand the notion of partitioning. So in between room, it's starting to put some amount of walls, right? We all know the notion of like having a living room and then having the kitchen with no partition. Well, he is looking into that notion too, right? There's no partition between the kitchen and the living room, and yet he's starting to, put walls around bedrooms so that bedrooms are like sheltered and or their own thing. The last thing he's doing at this step, which is really interesting, is understanding topological features. So this is the facade, and for some reason he's starting to understand that on the facade you want to see columns. So he's basically drawing for you the geometrical features, which are actually columns, and adding shafts at some places in the plan. Okay, so let's skip ahead and go all the way at the end of the training. At the end, after like 8 hours of training, I think it's pretty amazing. So it's not perfect. I'm not saying this is an amazing floor plan that you should take and bring to the client. I'm absolutely not saying this. But at the same time, what I'm saying is that it's 80% there. If you look at the adjacency of things in space, if you look at, this is the closet, this is the bedroom, this is the living room, you start to see that the relationships are way more sensible. It's way more sound. Again, those are the bedrooms, this is the kitchen, this is a corridor, those are the closets. It's not entirely wrong, right? There's some amount of intuition that we got inbuilt in the model, and it kind of abide by the rules that we follow as architects. Of course, you're free to tune this, right? It's not the perfect product, but it's a really sound base to start a design, let's say. So let's just look under the hood what we mean by AI models. So let's be very specific. The type of model I'm using, among all the type of models you could use, are what we call GAN models. So GAN stands for Generative Adversarial Neural Nets. There's a simple metaphor to understand what those models do. It's think about a student and a teacher. The student tries to write a paper, and then the teacher basically takes the paper and gives a grade to the student. Well, the same notion here. The generator, the students, the discriminator would be the teacher. What's happening is that the generator is trying to generate images, and the discriminator, the teacher, who knows what a floor plan is, takes the image and gives a grade back to the generator, telling him whether he did well or he didn't do well. And based on this, the generator adapts its performance and the quality of the drawing. And so over time, what you saw in the training sequence is simply the student getting better at writing papers. It's the generator getting better at drawing floor plans. So if you keep this in mind, then all the examples I'm going to show you will make way more sense. You understand where it comes from, what is the architecture behind this. So let's keep this in mind for the future. But before we dive into specific examples and demonstration of what AI can do for us, it's crucial to understand that there's a background to the story. And I'm not tossing AI on the table like this, saying it's a disruption and it's a new thing. It's actually not at all a new thing. It's coming from afar. It's coming from the history of systematization of our industry. Clearly, a long time, architecture has tried, some people have tried to systematize the way we design, to turn design steps into a process, for better or for worse, but at least it's an ongoing effort that has spanned across the last century. In that effort, you could see 4 movements: modularity, computational design, what you all know as CAD, then parametricism, and finally AI today. The type of thing that happened along the way could be kind of split into what we could call invention of theories, the world of pure ideas, and on the other side, innovation, which you could think about as being the implementation of those inventions, those theories. If you if you look at the graph, the one thing that is the key takeaway is all those tiny arrows and wires, connecting everything to everything. That just simply says that there is no disruption here. Anything borrows from the past, especially AI. If you look at all those arrows that just go back in history, basically, it's a constant incremental change. There's no disruption. There is no sudden big bang here. It's an incremental change of steps building on top of each other. Crucial to understand, again, because it's a long overdue that AI is in our field. It's not at all something that just fell from the sky. Another point I want to stress out, which is very crucial, is it's not also a horizontal sequence in the sense that that sequence, that change actually matters. I don't want to demonstrate the notion of progress tonight, because progress, as we all know, can shake the core of science and epistemology, as we all know, and it's an ongoing debate, what actually progress is and does it actually exist. But we can put forth a framework to understand whether in the world of generative design, there was some amount of progress, whether we actually are moving forward or backward, or is it just a stagnation? I want to propose this framework to judge whether we are moving forward. And so the idea is very simple. When you use a computer and you ask the computer to generate options, you're looking for two things. You're looking for a broad variety of options and options that are relevant. Variety simply means you want a lot of options, so quantity, and each option has to have kind of a singular nature. It has to be specific. You don't want 1,000 options that are all the same, right? So this is variety. Hopefully it's what you want to achieve. On the other side, you want relevant options, meaning you want options that are architecturally sound, but also that you can build. And that's the constructive feasibility. So those two matrices, right, variety and relevance, can be interrelated together to build like this variety times relevance matrix. The whole point of this framework is to say, if we take those movements and this notion of systematization of the industry, and we try to lay out where those movements stand in this framework, then maybe we can forecast or look into the notion of progress. So all of this is online, and there's publication and everything, so feel free to jump on Medium and look at it. Because I go on in those articles, I explain why I'm laying out those four movements the way I'm laying them out. But all we need to take away from this slide is that once you take those four movements and you lay them out on the variety matrix and the relevance matrix and you cross-reference them, well, you see progress. It's not a linear progress. Again, this is minus, minus, and plus, plus. So ideally, we would want to see something moving like this. It's not a linear progress. I'm not tracing a straight line. It's a jagged edge. But at the same time, even if it's a jagged edge, it's still a progress. We go from modularity to computational design to parametrism to AI, and there is more variety and more relevance in the thing we can generate. So again, I'm not trying to demonstrate progress as an abstract concept. I'm just saying, in the world of generative design, we're moving forward, and it's pretty exciting. So now I just want to narrow it down to something very tangible, so that we all understand what AI is bringing to us. It brings flexibility, options, and analysis. Those are three big threads on which I worked in my thesis, but also that got tackled in that we tackled at the Spacemaker department of R&D. And so let's dive into each one of those and just look in detail what we actually mean by that. So the first one is flexibility. So what you see here is pretty exciting. Those are some early results of my thesis. And so for each GIF, each frame of each GIF is basically a footprint of an apartment unit. Each time, for each frame, I'm giving that footprint to one of those GAN models, the AI models that I train. And I'm asking the model to do the infill, to draw the partition inside of the footprint. What is fascinating is that those algorithms were trained on databases of plants that were super mundane, canonical, very simple, like the most banal penthouse floor plan you could ever see. And yet the shape I'm asking the model to look into are counterintuitive or far from what the model has seen in the past. There's a stretch here. And what's very interesting is through this GIF, I'm kind of testing how far the stretch can go. And the answer is pretty far. It's not great. I mean, it's, again, early results. But there's some amount of logic in how he's laying out the shaft, the walls. He's handling the facade, making some openings, and how, take that space in the corner, it goes from being part of the living room and then it gets shoved into his own, I don't know, pantry, or it's like a side room. But the flexibility here is kind of demonstrated in the sense that as I change things and as for almost unfeasible topology, the model is still able to go at it and find some amount of solution, some amount of rationality and logic. The same idea here done for program. So it's not just about laying out the partition, it's also about finding the set of results, pretty fuzzy, I'll give it to you. But at the same time, if you abstract it and you look from afar, there's some amount of logic here. Things move with respect to some amount of architectural logic and let's say intention. But again, early results, not perfect. We want to go further. The whole point is to bring this to the architect. So here is a tiny interface I ended up coding by the end, where the same models trained further, doing better, were shoved into this tiny interface. And let's be very clear. What's happening here is that on the left of the interface, I let the designer draw. So in black, you draw the footprint of the apartment unit. In red, you ask for the position of the facade window. And in green, with the green square, you say, here's the entrance door. On the right, the model generates in almost real time, given layout and space of rooms and features and shafts and windows. Because it's so fast, because it is actually really easy to compute, then it becomes an iterative process. You ask for something on the left, you input your constraints, and you get a result. Then you tweak it again on the left, and you get an answer on the right. So it becomes this kind of iterative process where the human and the machine basically interact, and there's this feedback loop, this like interaction between us and the machine to nudge the design into a direction. And again, I'm not saying those plans are perfect. I'm just saying there could be a sound initial step to start design. It's just the spark, let's say. It becomes way more interesting now. So flexibility, we've seen it. There's some amount of flexibility in the way you can lay out rooms. But there's also flexibility in the way you could think about the design process. So in that thesis, the idea was to say, you could think of design as a series of steps, a sequence of steps. Each step could be encapsulated into one model trained so that the output of model number one would be the input of model number two, and you would train them basically. The reason why it's exciting to do that is that you can basically isolate pieces of architectural expertise within AI models while allowing in between the models for some user input. So see the thing. The point is not to remove the designer or the architect from the process, it's actually the opposite. If you chunk like this the design process, you allow for input in between. So the whole notion is to say, I have a site, model one is generating the building footprint. Then I let the designer change what the machine gave him or her. Then that gets fed to model number two, same idea. I get the program laid out in the apartment units. I can change that also. Then feed that to model number three and then get the furniture of the building. So as we go down this path, we retain control of the design process. At the same time, each model is being trained sequentially. And what's very interesting is that to maintain those models, to improve the quality of this pipeline, then we can go back at each single model and improve its performance. If I would have trained just one single model, there would be no way to unbundle, to decouple those, those different realities, right? And then to go back in the process and say, okay, I want to change that aspect of things. It's I'll go through the models and then we'll give it another degree of complexity. The first model, again, was doing footprint. So to be clear here, what you have is for each triple, you have the input, the output, and what was in the database initially. And so this is theoretically what the model should have predicted. Again, it's not perfect, but it's still able to guess what the output should have been. This is for the footprint. This is the way it's laying out rooms in space, so program, and again, color and code the program. And the final model was furnishing. So you would give him a given layout of rooms with a given program, and he would find a way to get the furniture in space with respect to the program. The idea is that you will never get a bed into a kitchen, you never get a sink into a bedroom. That's what you would end up having by the end. I'm going to make a small stretch here, is that it gets even more exciting when it gets tied to architectural concerns, things we care about as architects. So think about styles as being a function of this kind of strategy. You could argue that each style has its own way to tackle space, to tackle furnishing, to tackle room layout, to tackle building footprint. Well, then we could just train models for each given style and see for a Baroque style, for a row house style, Victorian, Manhattan units, how all those models performing. But not just performance. Well, basically, is this not a way for us to investigate the personality, the characteristics and properties of each given style? It's something we've been doing as architects for a long, long time. It's just that AI gives us a very clear investigative mean to dive into those topics in a very rigorous way. So it gives us the opportunity to use architecture as kind of a science of observation. We can just dive into all those topics, all those research threads we like as architects, but with a new lens and a new rigor. So it's basically what I did in my thesis. So I looked into those 4 styles, and I looked into 6 abilities of style. So very quick, the ability to handle depth. So if you have a deep plot, compactness, how compact are things in space, or is the program compacted, or is it sparse in space? Then the orientation, is this given style able to handle a single orientation, a single facade, versus multiple orientation? How does it handle acute angle, like sharp angle in the plot? And what is the program spectrum? How wide is the program? Anyway, I didn't draw those things before the thing. I trained the models on each given style and then draw this based on what I observed in each one of the styles. So let me show you the image of what I mean by that. Here is the result. So on the left, you have the training set for the Baroque style. So it's just like it's a subset of it. There was like 800 images of Baroque style spaces. And these are generated units with the weirdest possible shape of the plot. Absolutely nonsensical, but it's the whole point. The whole point is to say, can I test out the ability of a Baroque style to handle acute angle, depth, single orientation, multiple orientation? It's just a game. I just wanted to see what you could get out of it. And it's super interesting, right? Because the Baroque style handles, for example, acute angles really well. It goes at it and it kind of carves into the angle some amount of alcove. So it would go at this tiny angle and carve something into it, and that would end up being the bathroom. Moving on to like another style, the Manhattan units. So you have just a single orientation for the typical Manhattan units. And therefore, in the generated units, if you have multiple orientation, well, the flat itself will be orientated towards just one of those, as opposed to this one style, which is like row house. So, two floors on top of each other. I challenged almost the algorithm to find a way to infill the plan before mismatch, right? I mean, the lower floor would be this kind of weird L-shaped thing, and there's a square on top of it. This one will go that way, this one goes that way. The whole notion is to say, this is not examples that the model has seen before. It has seen this kind of things, shapes that overlap pretty well, that match each other. And suddenly, we are asking him to reconciliate floor plans on shapes that have nothing to do together. And it's working pretty well. He's finding where to put the stair, how to also, very interesting, how to distribute the program across floors. Because there's a notion of program, right? I mean, we're still here. We still need to know what the living room is, the bedrooms are, and he's still able to make the judgment call and say, okay, I think it's better to put the bedroom upstairs and the living room downstairs. I think it's interesting. And then the last one is Victorian house. Well, most Victorian houses are freestanding in a field, and so they handle multiple orientation really well. And so when you test them on plots that have multiple facades, well, they are able to handle this multiple orientation really well. You've got hinges moment like this, where the thing is basically giving you one orientation, and then after the hinge, a new orientation. Same thing here, for instance. Is orientating things toward this one facade and then towards this one facade. So I'm just saying, through those AI models, we can just look deeper, into things we already think we know. The notion of studying architectural styles can just be turned into this quest of the rule. And the thing is, like, styles is full of rules, and I think there's a formalist way to look at styles, but there's certainly a way to look at stuff through the notion of function. And AI brings new means. It's just super exciting to look into those things. So those were some results of the thesis. I want to move on to the second thing, which is AI brings the ability to carry more options in the design process. So those are the interface of our software we have at Spacemaker. And we have, let's say, 2 sides of it. There is Sketch, and there's Generate. So it's a web app that helps architects draw, volumetric, let's say, to do feasibility study. And so the whole idea is that as you draw things in the Sketch app we have, you get offered options along the way. And so the architect is drawing something, and at the same time, some AI model running in the background is generating things that kind of match the need of the plot, and that resemble things that the architect has drawn before. So there's a back and forth between, I draw something, I get propositions here that I can bring on the side and save on the left. So you really see how tangible it is, right? You draw something, and a set of options proposed to you. One thing that is crucial to understand is that parametricism was only able to do for a set of inputs, a set of set parameters give you one output. There was a way, of course, to grow around a given solution in parametricism. You would have one option, one solution, one output, and you could find solution around this one option. So you could create diversity just by expanding from a given solution. But the control you would have over that was very, very slim. Here you can create, again, variety and quantity, or let's say, sorry, quantity and singularity at the same time. And in a control fashion, which is fascinating. You have 8 options here. We could go up to 1,000. And this is what the next bit of our software does. The whole notion here is that we turn the concept of sketch upside down. Instead of saying, I'm drawing something, give me options, I'm saying, I'm giving you a brief, I'm giving you constraints, give me solutions. So you set up a site, you set up the wind speed, you set up the constraints in which you're playing, and then the thing returns to you a set of options that can potentially fulfill your need. And playing the video, the whole idea here is to say, well, I've asked for options, is returning me a set of options ranked given to a set of metrics that I can then filter, and then later on I can just browse through all those options that are all tied to a set of specific characteristics. What is very interesting is that you could have thousands of those, so again, way more options, but also in the generation process, we are able to control concepts that are more granular and closer to our concerns. So the notion of typology, topological features, geometrical forms, are things that are quite hard to encode and to teach to a computer. Well, AI does that really well. Parametricism had a hard time to do that. So another way to phrase this is we could generate options with respect to square footage, with respect to perimeter length. My point is with respect to some numerical value. It is more interesting, at least for us architects, to generate things with respect to topological features, typology. And this is actually what it's able to do. Not only is it able to generate options that are tied to realities close to us, typology, topological features, etc., but also then later on you can filter those options based on the same notions. So say you like a given typology, you like this type of building, and you like this type of building, and you can filter out the search space and narrow down the search with respect to characteristics that matter to us architects, not just numerical value that are remote and foreign to what design actually is. Moving on, the last step of the triptych is saying analysis is the last form of generation. So far, we've seen that AI gives you more options, more flexibility in its ability to generate geometries. If you think about analysis as a generation process, well, you understand that AI definitely brings something. So the way we've been doing things in the industry so far is to say, well, I have a problem. I'm going to simulate the problem. By that, I mean, for example, for wind speed analysis, typically this wind speed analysis, I'm going to ask the computer, given a set of parameters, to compute precisely the exact value of each single tiny pixel in this gradient and return to me something perfectly accurate, or at least as accurate as it can be. It takes 10 minutes. It's computationally very expensive, and therefore it's a hurdle. It's a hard stop in the design process. What is very interesting is that you can turn the logic and say, well, maybe I can guess the outcome of the simulation based on a set of inputs by doing a statistical modeling once again. So this was done in 0.05 seconds. It's just a way, we're just democratizing simulation right there. This is not accurate. It's just good enough. But again, you don't need something perfectly accurate. We're not designing a plane, we're doing a building. And so as we don't need search and accuracy, well, we can play on the trade-off. We can lower down the time needed to do it. We can sacrifice accuracy and just have a best guess. It's more than enough. And what it enables you to do is that we can shift this back into the design process and say, as I design something, can I get live feedback? So you see this one architect trying to study the volumetry of its design. Well, he's basically getting a live feedback of the performance. And because he's getting this, well, it completely changes the way we interact with the notion of performance. You don't need to run through a consultant all the time. You don't need to wait on timelines and everything. No, you at runtime, as a live analysis, you get feedback on your design. And again, that done through AI. So it's kind of the last chapter of what it brings to us. Flexibility, option, and analysis. So I want to wrap up the talk on this notion. I think it's kind of crucial to understand this. First thing, AI is not like a new dogma. It's not a new disruption thing that's going to automate the architect's job and everything. I think it's really not the point of tonight. what it does, it tackles the depth and the complexity. So there's this one quote by Rilke that I think is really interesting, is to say, in the depth, everything is a law. So the intuition of parametricism is to say there are laws, there are rules that we can explicitly declare. The one thing is, and to Rilke's point, there's depth to it, there's complexity. You can't just pluck rules out of thin air. Most you can, there's no problem. There's certainly a way to think about design explicitly, but there's a certain complexity to it, and certain things that just can't be named. And also, there's a gray zone between the thing I can't name and the thing that is way too easy to name. And this in-between, this gray area, well, that's what AI can bring us. It's a way to tackle the depth, to handle complexity, and to encode those parameters, those rules that are counterintuitive, and yet at the same time absolutely crucial to the design process. So again, reflecting on the code, I think it's very important to understand we can handle complexity in a new way. And last point, we can bring architecture back to something it used to be at the Renaissance, which was be a science of observation. There are rules to the thing we do. Observing those rules is a valuable thing to do. And maybe AI can be the way to go. Before we turn to Q&A, all the things I've been saying tonight, all of those are in publications, so feel free to just go on Medium and everything and just read those, and I'm happy to answer any question of those in the future if you have things you want to know or you want to be clarified. That's the end of the talk, and I'm happy to open the floor to questions. Thank you.
Wonderful, Stan. Very impressive. Thank you very much. We would like to open it up for Q&A, for questions. Anybody would like to jump in? Yes.
With how often, like, there's always like fears of automation, especially with the creative process. How your thesis was specifically received, because I think it was a very precise in its like application of like not of still giving like agency to the architect. I wonder like, yeah, and I think you're also like very careful to say that like this is just giving you options. It's not like giving the design. How that was taken by everyone in this institution, yeah. Yeah, specifically.
No, yeah, no, it's a really good question, because I think it's one of the biggest limit to this kind of new techniques, right? The reception of it will condition completely the way we actually use those things. And so, to answer your question, it was taken well. My advisor was Andrew Witt, which helped a lot because he's amazing and was perfect to stir the discussion and help steer the thing in the right direction. At the same time, yes, there was some pushback and pretty awful pushback. But I understand why, and the reason of the pushback. I think the discussion today around AI in other fields, in adjacent fields, can be a bit scary and a bit too removed from the reality. I think there's a way more rational way to answer questions. When it comes to architecture, that's what I was trying to do tonight, is just to show the tangible things. And the tangible things still need the involvement of the architect and the designer. For the simple reason is that, again, the quote of Rilke, right? This notion that there is complexity, there is depth. There are things we can name, things we can't. There's an in-between, a gray area that AI can tackle, but there's definitely things the machine can't do and can't name. And that we still need to be there to actually do it. Does it answer the question? Awesome, thanks.
So I have a question. You spoke about when you showed like the Baroque style, it could like create more outputs for you. And I guess I'm thinking like if you showed it something, could it innovate on that? Like could you show it like a 70s apartment and then you end up with like open floor plan? Or like what do you need to feed it for it to become innovative?
I think it's important to understand there's no creativity. there's no notion of we are the creativity. These things just make solutions. So it's through the difference between a creation and a solution is the cultural significance of the solution. We condition the cultural significance of the solution. It will only be creative if we think it is, and we stir the thing towards a creative place. and a culturally significant space. The thing on its own will never do it. Although, one thing that's really interesting, and it's, let's say, one step forward, is that here, those GAN, right, were only trained on like homogeneous database. Take the Baroque style, it was only trained on like Baroque style floor plans. You could start to change things, right? You could hybridize the training set and say, okay, it's going to be 50% Baroque, 50% Manhattan units, I don't know, and you see what you get. And the thing for you would start to make a blend, and it's very interesting. Although it will make a blend with this kind of model I used, but you will have no control over the way the blend is being done or how you can play with the blend once you generate new things. There's a new type of model that came out, I'm going to say something wrong, 2 years ago, 1 year ago, called Style GAN. Style GAN is a very super sexy idea, is to say the blend happens, but you still retain control over the way you hybridize things. So say we're training with a training set of 4 different styles. The machine, as it's learning how to draw floor plans, knows that the distance of a given solution to each one of the 4 styles given in the training set. Then, once you want to generate an apartment, you can specify what mix you want. It could be 20% Baroque, 30% Manhattan, I don't know, 30 and 20 of the 2 others. But the point is, you can choose the blend, and it's very interesting because then you keep the control. And so the thing that is being generated is still a solution, but your agency and your ability to make this a creation is completely empowered. So again, solution creation, the same thing. So, yes.
Hey, first I would say it's a fantastic thing. Like I've read your things in Medium before, but I always had some questions, so I'm just gonna try to do it in 2 questions, more or less. If that makes sense. The first one, I guess, is like from your how much is or how the curation of the data library works. You know what I mean? Like, where do you get all these plans from? Do you actually draw all of these plans because they need to have a certain representation, right, for the machine to be able to understand, etc. So that's one question, I guess. And then the other question that I have, that I think I've always had in my mind, more or less, but maybe you have a different philosophical approach to it. Like I don't feel like I have a problem with AI or all of this kind of thinking at all. Like I'm a designer. I have nothing to do with technology whatsoever. I don't even know how to use a grasshopper. But my question is that but my question, like what I always thought and discussed with friends that are in the tech program as well here, is the idea that I think that, like, let's say 98% of what is built out there is kind of a model of AI, right? There's certain logics to the things that are built, but nothing is really interesting unless it produces like an accident. Like it's something that nobody would have imagined before, and because it's kind of different constraints and problems, it produces something different. That's what I think, like the idea of the accident, and then the questions of the.
No, no, no. Pleasure. For the data, I think it's interesting, easy to answer. So there is more and more repo online with like actual, floor plan database. So there's one thing I can point right now is there was a research paper from Washington University with a database of vectorial floor plans. So not pixel floor plans, but vectorial floor plans, which allows you actually to have access to the geometry and to be able to generate training set however you want with the same graphic standard, right? So my point is to say there are resources out there for you to actually play with. This one WashU paper I think is interesting. On GitHub they have a repo you can play with. So it's getting easier by the day to actually have access to sufficient data to actually do that. For the GAN thing, some of the GAN models, the typical one is pix-to-pix. The facade data set I think is 800 images. I might be wrong, but it's not that data intensive. Style GAN is way more intensive. I think 40,000, something like this. So for the simple GAN models, you can still play around with few data points. Okay, to the second one. Sorry, your question was accident, right? The accident, yes. Okay, so the question was like, what about if we can create accidents with AI?
Kitchen, but I never think of that. But the AI, because doesn't really know how to model things,
Mm.
it produces that, and then I can work upon that. Rather than having it me say, this is an interesting Baroque plan for New York. You know what I mean?
For sure. So basically, we'll go back to the question from before: solution versus creation. It gives you a solution. You're the interpreter of that solution, whether it is relevant or it's irrelevant. Um, there's something that keeps happening in our discipline is the fascination we have for irrelevant things. We love irrelevant things. The weirder, the twistier, the more. Anyway, you see what I'm getting at. Yeah, well, we love it. And the thing is, I think there's definitely interesting things that can be created for those models. I really hope it's not going to steer us even more in this path of irrelevance and also on the path of not contributing. Because there's the thing, right? You can contribute to society with those models and bring new ways to design space. You could even do typology research. You could train the thing on an array of typology and see what the blend of those typology could look like together. But I really sincerely hope that as we use those models, we will strive for relevance and to contribute to society and not try the thing we, again, love to do, which is play around and have weird things.
Relevant, right? It's the idea, for example, of an open kitchen attached to a living room. That someone 100 years before would be like, this is fucking crazy. Nobody's going to do that. And then somebody might have stumbled upon it like an accident and said, wait, this could actually work. I could design a certain way.
Typology research, absolutely an option. Especially when it comes to style GAN thing, you can actually tune the relative weight of the influence you have on the thing.
Mix models more than just because usually how these models work, at least from like data training and subtract vehicles, stuff like that, is the idea that it learns from all of the inputs that it has, right? It can produce normally something outside of the inputs that it has. It's hard to do.
Sure.
But if you mix models, you can start to create something.
Oh, absolutely. Absolutely. Solution.
So with Spacemaker.AI, when you guys are pulling your training sets, so it's kind of at the urban design scale, how significantly scaled are the training sets and numerically, and then where are you pulling them from?
Data points we have.
Yeah.
Yes. Sure.
Yeah.
So I don't know how much I can disclose, but I'll try to. I'll try to be as as transparent as I can. So the idea is there's many ways to get these training sets. One thing I can refer to typically is the thing I've done in my thesis, right? The building footprint generation. So the first model in the wireframe, right? So the first one, you can simply use GIS data just for the to generate building footprints, right? The amazing thing with GIS data is that it's absolutely clean. It's pristine data. It's accurate, cleaned, and labeled with land use. So my point is, since it's labeled with land use, you know the type of shape your model is learning, right? So I had a whole array of models. One was trained for like retail buildings. One other was trained for like housing buildings. You could even cluster it by type of housing buildings. Like is it triple decker? Is it like a condo or something? Well, the point is to say it's great because in our field, one thing we know how to do really well is to keep record of data, and GIS is like an infinite tank of clean data for us to play with. It's very easy to bring into Python, to turn it into a training set, at the press of a button, and then to start training on it. And then I know you said numerically for the first model, I think I had, I want to say something wrong. I think it was somewhere between 800 and 1,200 images.
On a kind of local basis or something.
Yes.
And then expanding them.
Yes, absolutely, absolutely. You need to cross-reference the plots and the building on the plots, but with simple, ArcGIS queries, it's actually pretty easy. Yes.
I think I got this from somewhere, but Spacemaker also takes into consideration the real estate market, does it?
Real estate.
Yeah,
Real estate
market analysis.
So to be clear, you mean rents prices and sales prices, for instance? Is that?
That we're talking about what is apt for that plot and taking that into consideration.
We're not yet into the financial side of things. It's mostly into the, physical performance, sunlight, daylight, wind, etc. Less so on the financial side, but we're looking into it right now.
Thank you for the presentation. So my question is more about the genesis of your whole project. Like, were you always interested in AI, or at what point did you think, oh, it would be really beneficial to architecture if you combine AI with architecture? Is there like a backstory or motivation for like doing the whole project?
Yes, no, yeah, of course. So I think I think the start of the project. So I started to take classes, right, like data science, machine learning at MIT, and things like this. There was an intuition, right, that there might be something there to be done. And then I had a lot of friends who were doing data science, and I was seeing how they were able to generate things that were relevant. And in this one workshop that was done by NVIDIA here, it was super interesting. They were generating time series for, I'm not going to find the right words, hospital dismissal. So they were basically able to predict time series to know when patients might leave the hospital. And there was a generation aspect to it that I thought was amazing. And also the completely mind-blowing thing is that they were not just predicting, they were turning the data into an image. And then you were generating an image, and the image was encoding numerical values. So you were basically going through an image as a representation as an abstraction of the data, and then back into the numerical space. But the thought was, okay, wait, but let's stay in the image world, right? Because that's what we handle as architects. So, and they had those generation models that were just fascinating. And so that was the spark, let's say. There's one thing I wanted to touch upon I think is really interesting. So it's about abstraction. So this notion that through those AI models, there's a way for you to build bridge between different abstraction levels or between different types of representation, which is super exciting for us because the only way today, the major way for us to represent buildings is geometry, right? Like images, 2D, then 3D, of course. Then BIM adds a layer like grammar on top of it. But there might be other ways, other abstraction levels that we could map things into. So typically, you could go from a geometric representation of a thing to a semantic representation of a building, which could be very handy to handle high-level ideas. There are concepts that a building convey that we want to embed in the building and then we think of as we design buildings. And yet, if we want to convey those ideas, the only handle we have on the building is geometry. So you push and pull columns, you push and pull walls to convey an idea or a concept. But an AI model could basically help you to learn the mapping from a high-level concept to a geometry. I don't know if you see the power of the thing, but the whole idea is to say, we can build bridges with other spaces, other level of abstraction that can help us tackle higher level concepts. And since in architecture we love to talk about like the high level picture, the grand scheme of things, there might be a way for us actually to operate at that level through our computers, which is a super exciting thing, and AI actually can bring that.
In that vein, what kinds of data sets do you think need to be produced by architects, perhaps, that are suitable for that kind of higher level translation? Because you probably can't build it out of just like Baroque plans things.
It's a very good point. Yes, so the thing is, the challenge is to find a way to turn a building into a semantic graph. It might seem a bit, so a graph, right? A graph is like nodes and connections. So finding a way to turn any ontology, let's say object, into a representation that talks about the different parts that makes this one object and the relationships between those parts. So the challenge here is for us to be able, as architects, to find a way to translate objects into those graph of objects and relationships and to qualify the relationships. It's not just going to be word, let's say, it's going to be adjectives and verbs. Those are the high-level features we need to be able to produce, to be honest with you. I'm not clear yet how we could do it. We could use inference model to infer from a given context what could be the concept that connects things together. There's a lot of work done in NLP, natural language processing, that can actually help us do that. And I'm actually pretty confident we could do these kind of things. But a very simple example, if you could have a 3D representation of a building and its translation as a semantic graph, and you could both change the project through the 3D representation of the building or through the semantic graph and change relationships or high-level concepts, and that would directly be translated into the geometry of the building. So yes, I think generating the semantic graph. I don't know. I don't think. I'm not sure. I wish no one.
I have a couple of questions, and perhaps we can wrap it up. I like how you talk about the idea of representation as inherent and very powerful and very important when you are working with artificial intelligence and machine learning. How you represent that data, right? And there's a tendency within architecture. I used to be an architect. I know a lot of architects. And when you draw and you have like the object snap, like I think there's like an obsession with precision in the drawing and the design process that is in very strong contrast with a lot of how these models work and how they're represented internally, because mostly they work with images and with matrices of pixels as data sources, and what they yield is like this like blurry, fuzzy, unbounded, like soft kind of boundaries, which are not at all like part of what we work with. So perhaps like in the same line of the question before, like what kind of resistance or like have you found in the community with this like kind of fuzzy architecture that these models can produce? That's question one. And question two is, what is next for you in terms of work professionally? What can we expect from Stanislas Chaillou in the next year or two?
Sure, thanks. Okay, the first question is a really good one because bringing, so the thing is we represent things in a continuous domain, right? The whole notion of those GANs is that we generate images that bring a representation that is necessarily continuous, meaning it's fuzzy. It's not, you're not playing with increments, you're playing with something continuous. The value could be 1.050633, when discrete representation would be increments 0, 1, 2, 3. So that doesn't play well with what we experience in construction when it's all about discretizing the building into elements of fixed parts. So discretization is at odds, right, with the notion of generating in a continuous domain. So to solve that, first of all, vectorizing a continuous object is the first challenge, turning it into not pixels, but like actual geometric objects is the first thing. And the second thing is, yes, there's a snapping thing to be done, meaning as you take a continuous output, you want to be able to rationalize that output and bring it into the, bring it some discreteness. So typical example, you generate a floor plan. You want to snap to the structural grid. You can't just have a wall fall between two lines of grid, right? So there is a step that comes after that is very much an optimization. And so that's the final, actually that's an article I'm working on, this notion that GANs and those models bring an amazing initialization. So the whole paradigm of optimization is to say, you take an initial step, you initialize a system, and then you go down the gradient until you find some amount of fitness. The fitness is basically that sweet spot where the thing's performing. That gradient descent, it will work really well if you start from a sweet spot. If the initial layout at the beginning is actually sound. Well, it was very hard before to do this, and a lot of optimization were randomly seeded. This seeds the thing in a very sweet spot. Therefore, you can go down the gradient and end up in a really nice place. So yes, we need to discretize. Yes, we need to vectorize. But let's not forget that the beauty of a continuous domain is starting at a better place when we optimize. And then the question you were asking, the other one. So, yeah, well, I work for Spacemaker, so I'm going to work even more for them. We're pushing more of the R&D office. Yeah, time to say that we are hiring, so do reach out because we are actively hiring people. And it's super exciting because basically what's happening right now is the company, well, it's basically doing really well. We have the opportunity to, as a small team of 6 to 7 researchers, to shape the vision of the company in terms of midterm to long-term goals, and to set up the research threads. And it's a really rare thing in the industry. Often, when you are in R&D, you try to catch up with competition, with realities coming from the top. And in our case, it's kind of the other way around. We're kind of leading an effort, which I think is really exciting. And so, and we can publish things. So I might have done a PhD, but to be honest with you, here I've got the opportunity to look into interesting things and to publish those things. So I think it's going to be more of the same. And yeah, look out for new publications. They're going to come soon. Thanks, guys.